Okay, welcome back. So we're looking at the second lecture of Mass Spectrometry Basics with me, Lennart Martens from Ghent University and VIB. In the first lecture, as you will remember, we talked about amino acids and proteins and how the different properties of the amino acids were relevant to study in the mass spectrometer. Now today we're going to talk about the instruments themselves, the mass spectrometers. And for that, the first thing we'll do is give you an overview of the basic components of a mass spectrometer, and then we'll go through each of these components in detail. Now, each component will have its own dedicated lecture for it. And we'll start today with just the overview and the ion sources. And that will sum up this lecture. So without further ado, let's get started. So a mass spectrometer can be generalized as follows. And this goes for nearly every mass spectrometer. They will have been built around an ion source, a mass analyzer, and a detector. So each of these components has a very important role to play. Essentially, a mass spectrometer, or the analyzer part of a mass spectrometer, is a highly precise set of scales. And they weigh very small quantities of mass very accurately. Now, the way to do that is to use electrical fields. We're not going to use gravity for this, so not like a kitchen scale. We're going to use electrical fields. And when you use electrical fields, you need to work with ions, because only ions feel electrical fields. And so it's crucially important that you take your analytes from the sample of interest and get them into an ionized state. And this is what the ion source takes care of. So the ion source is crucial in getting us ions, because everything that's not an ion is not going to work in a mass spectrometer. And then the analyzer is going to analyze the ions for their mass, and then that is going to be, in the end, is going to be confirmed by the detector, which has essentially the function of figuring out that something was there to begin with, and that allows us to back calculate the mass. Sounds a little bit complicated, but we'll get through it step by step. I use a color coding here, which I will use throughout the slides and throughout the lectures. It's always going to be the same color code. So this light blue always indicates sample or sample molecules. This purple gray is ion source. The green is a mass analyzer. The red is a detector. Only on this slide am I going to talk about one other component, which is the digitizer. Now, the digitizer is an important component of a mass spectrometer and used to make a lot of difference, but these days it's not that important anymore. What does it do with digitizer? Well, you have to keep in mind that your mass spectrometer is essentially giving you a continuous signal ultimately, because the detectors that are responsible for generating the signal are like voltage meters. We're talking about ions, and so these ions are going to ultimately hit something and generate a current. And this current, like on an oscilloscope, we're going to track the changes in this current. And of course, a high current means many ions, a low current means few ions, and no current or a background current means no ions, nothing happened. And so when that happens, we get a continuous signal. But it's very hard to work with continuous signals. Instead, what we would like to work with is a discrete signal. We want to say at a given time point we have this much, at another time point we have this much. And what we need to work with digital signals or discrete signals is we need an analog to digital converter or ADC. And essentially what these things do, just to make it very simple to understand, is they take an analog continuous signal and they sample it. So they check what the height of the signal is at a given time point, write that down, then move a time point on, take another sampling, write that down, and this set of discrete observations becomes your digital or discretized signal. Now, the speed at which this happens is really important, and that's where the digitizer comes in. Suppose you have a slow digitizer, and we have a curve that spans roughly this. So there's a signal coming in and then going down again. If we have a digitizer that measures at this point and then is going to be silent for a while, and then it's going to measure again, because that's as fast as it can go. It's going to measure a small amount, a large amount, and then a small amount again. And then the problem is, for this beautiful curve, we only have 3 points. So the closest approximation that we can do is just make a triangle out of this. Now, in this particular case, it's not too bad, but imagine if the original signal were like this, with a bump in the middle. Then we would measure it here, here in the bump, and here. And so what we would get is we would get a very small signal, and we would be completely oblivious to the 2 peaks that flanked this valley where we had the measurement. If we had a digitizer that were faster, it would have been able to measure it here, 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 here again, here again, here again, here again, here again, here again, and we could have reconstituted the original signal. So in a way, what is important here is that the speed of the digitizer, so the speed with which it cuts continuous time into small intervals, is very important for resolution, how fine-grained a piece of structure you can pick up when you go through the signal. And so that's where these things used to make a lot of difference, because they're essentially computers with an internal clock, and clock speeds are measured in gigahertz or megahertz. And some of you may remember that back in the day, and I'm talking about 10, 15 years ago, computers would tick at clock speeds of a few megahertz. And so that would be very infrequent compared to today's computers, which measure in gigahertz. And there was a way of upgrading the resolution of your mass spectrometer by upgrading this digitizer. You could go from a 500 megahertz digitizer to a 1 gigahertz digitizer, and you would double the number of sample points, and you would double the resolution. So something that looked like point would now start looking like point, which is much better. So that was in the old days. Nowadays, these things have become so fast that the rate limiting steps for the resolution are actually here and no longer in the digitizer. So that's why it's important to know that a digitizer exists, that it takes an analog signal, chops it into small bits, and makes a digital or discrete signal out of this continuous signal, but that's about it. It doesn't really affect the instrument that much anymore. So with these components that we have highlighted now, we know how a mass spectrometer is built. Now what is very important is that we understand how each of these components actually works in real life, because they come with their pros and cons. And today we'll be focusing on the ion source. And remember, the ion source is crucial, because anything in the sample that is not ionized by the ion source will be invisible to the remainder of the mass spectrometer and will be lost for analysis. If your ion source is down, your instrument is useless. Okay, so it's very important. So let's get started with ion sources. We have two different types of ion sources. The first one is the MALDI ion source, or matrix-assisted laser desorption ionization source. So let's have a look at how this functions. We do have a target surface, which is a very simple stainless steel plate, small metal plate with a few pre-spotted circles on it. And there you deposit, with a pipette, you deposit a small amount of your sample, and remember sample is in blue, along with a chemical known as a matrix molecule. And there's lots of matrix molecules here, and they spread out through your sample, and they make a kind of mesh of sample, molecules, and analyte, and matrix molecules. Now, what is important is that this is solid phase. In fact, it crystallizes out on the plate. This is why we need a solid support. We're depositing a droplet and then letting the liquid, the solvent, evaporate. The solvent typically is water with some hydrophobic substance in it. And then we let that evaporate, and as it evaporates, this crystallizes out on the plate. So it's solid state sample with matrix. Now, that's all well and good, but this is completely useless for a mass spectrometer, because a mass spectrometer doesn't work on solid state objects. It works on molecules in the gas phase, preferably in a very high vacuum, so that we have nothing there but the analyte molecules and as little else as possible. So how do we get these guys into the gas phase? And remember, we still need to charge them as well. So we have two tasks: how to get them in the gas phase at high vacuum, how to get them charged. Now, that's where the LD comes into. So just to recap, MA is matrix assisted. We have matrix and it's going to help. So that's matrix assisted. Now we're going to do laser desorption. Laser is literally for the laser that we're going to use. So we actually have a laser here that shines a beam of ultraviolet light, or light, at about 200 nanometers somewhere, and it's going to shine onto this mixture of matrix and peptide analyte. Now what's going to happen is this matrix molecule is going to absorb the light, the energy in the light from the laser. And then what happens is when a molecule like matrix absorbs the radiation, it's going to vibrate, because energy is vibration. This vibration is going to get so extreme so quickly that in fact it is going to yield an explosion. So the whole thing is going to blow off the plate. That's desorption. It's a fancy term for blowing off the plate. And instead of absorption, you have desorption. So it's going to blow up into the vacuum, and that is where we get the gas phase formation. Okay, so this is a bit like Star Wars. You're literally shooting lasers at a target, and the target blows up. Now, when that happens, this desorption phase, we now need to do the final bit of our MALDI acronym. So we've got the matrix that assisted us when the laser desorbed the sample. Now we need to ionize it. So here too the matrix is going to help. Because the matrix is actually positively charged, it is a very good proton donor. And what is going to happen is that one of these molecules of matrix is going to transfer its positive charge onto the peptide. So we don't really know how this chemistry works because it's in a high vacuum, high energy chemistry. It's very difficult to study that in detail, but somehow an interaction, a bump between a molecule of matrix and a analyte molecule is going to result in one proton being transferred. The net result of this transfer is that we're now going to have a bunch of matrix molecules there, one of which has now lost a charge, and our analyte molecule or peptide with a charge. Now, very important in MALDI is that the charge for peptides, at least, tends to be 1 and only 1. So a peptide gets a single charge, positive charge, nothing more. If you were to study intact proteins, however, they are much bigger and they can accommodate many more charges. So a protein in MALDI can have more than one charge and will likely have more than one charge. But for smaller molecules like peptides, which by the way tend to be around 10 amino acids long on average, these will have only a single charge. This becomes important later on. So as you can see, MALDI is really true to its name. We use matrix together with the sample to assist us in laser-guided desorption and then ionization through the matrix. So it's a very good name for this entire process that is pretty violent, but is still known as a soft ionization method. Interestingly, Koichi Tanaka got the Nobel Prize back in 2002 for his discovery of MALDI as applied specifically to large macromolecules, in that case a protein. Two other names that you should associate with MALDI are Karras and Hillenkamp, who really pioneered the technology itself, but primarily for small molecules. So matrix-assisted laser desorption ionization. Another thing to remember is that this is solid deposition of the analyte, and in fact this plate can be archived. When you shoot the plate with the laser, you can actually see little spots where the target and the matrix are being shot off the plate, but you could take it and freeze it and keep it out of light and frozen for a while and then reanalyze it afterwards. So the sample is kind of archived. The downside of MALDI, I can also tell you that immediately, is that the MALDI plates need to be manually inserted into the mass spectrometer and then have to be brought into a high vacuum. Because all of this happens in a high vacuum, as you can see, because we needed to get the gas phase in the high vacuum. And that takes time, that takes manual effort. It's not something you can run easily 24/7. So there is a rate limiting step here in preparing the plate, which can be done by a robot, and then loading the plate into the instrument, which is possible with a robot, but it's very expensive solutions, and it's not used that often. But this is how the technique works. Let's talk a little bit more about the matrix, because it's interesting to see how they are composed. There are three types of matrix molecules that are commonly used in proteomics studies. There are others that are being used in small molecules, but we won't discuss those here. These are alpha-cyanohydroxycinnamic acid, or alpha-hydroxy for short, because it's a pretty long name, synapinic acid, and then 2,5-dihydroxybenzoic acid, or DHB. It used to be that alpha-cyano was the go-to matrix molecule, but these days DHB is probably more popular. Now, all three of them share similar properties, so let's have a look at the shared properties here. They all contain a benzene group. This is very important because the benzene group is actually the thing that absorbs the UV light. This group will take all of that laser light and turn it into very violent vibrations that result in an explosion. So it is exactly the matrix that explodes, and that's the whole point, right? Remember, we don't want the protein or the peptide to explode. We don't have anything left to analyze. We want the matrix to explode. But while the matrix is exploding, it should bring the peptide analyte with it. And in order to do that, it would be really bad if all the peptide were at the bottom and all the matrix on top, because it would blow off and not take the peptide with it. So instead what we do is we try to make as best as possible a layer cake with a lot of matrix and peptide stacked on top of each other all the time, so that when a bit of matrix blows up, it automatically takes peptide with it. Now, there's something interesting about the patterns that these molecules with benzene groups form when they are crystallizing, because the benzene ring is flat. And so when it forms a crystal structure, it tends to form flat layers, just like a layer cake. Now, that is a good property because you get layers and then the peptide ions can be embedded between the layers. But there are also some amino acids, which you may remember from the previous lecture, that do have these aromatic rings. They're phenylalanine, tyrosine, and tryptophan. And these amino acids, because they also have a flat ring, they can fit really well with the matrix sheets that are crystallizing. So they crystallize really well, they transfer the energy really well, and as a result, any peptide that contains one of these three aromatic residues is more likely to be seen in a MALDI experiment than a peptide that does not contain these. So there is an inherent bias in this technology that is biased towards peptides containing amino acids with benzene rings. So that's something to keep in mind. The other thing that they all share is a carboxylic group. And you know why we have a carboxylic group? Because we need an acid that will donate a proton to our peptide. And here you can see where the proton donation comes from. The carboxylic group needs to be there. Some of them actually have conjugated double bond systems that help them absorb the laser light even better and make this a little bit more acidic. These differences are minor, we won't go into the details. The final thing that you may notice is they tend to be substituted with oxygen molecules or nitrogen molecules. This is to make them soluble in the same kind of solvent we use for peptides. Now, peptides don't like pure water. They like a little bit of hydrophobicity in their water. And these molecules are pretty hydrophobic, so we make them a little bit more hydrophilic. As a result, the semi-hydrophobic, semi-hydrophilic solvent that peptides like is very similar to the solvent that these molecules like. And we can see that here in the summarization. We need small organic molecules because they're small and simple to work with. They should co-crystallize with the analyte. Remember the layer cake. They should be soluble in solvents that will also dissolve our analyte. Otherwise, we could never get them together on the plate. They should absorb the laser wavelength. This is crucial. Otherwise, we don't get the explosion. We don't get the desorption. And they should cause this co-desorption of the analyte, which will happen if the matrix absorbs the laser light to get the energy, and if, of course, they are soluble and co-crystallize with the analyte, this is automatic. Finally, they should promote analyte ionization, hence the carboxylic acid that they all contain. Okay, so we've got MALDI covered now. Now, MALDI isn't used that much anymore because of the problem I talked about earlier. It's very difficult to automate MALDI. Instead, this method is much more used. Before I explain it, I told you that Koichi Tanaka received the Nobel Prize for invention of MALDI. He actually shared it with John Fenn, who got the same Nobel Prize for easy ionization. The third winner of that year's Nobel Prize was for the invention of NMR. And they split it so that half of the prize money went to the NMR invention and the other half went to mass spectrometry. 1/4 thus went to Koichi Tanaka and 1/4 went to John Fenn. So it was a three-way split, protein analytics Nobel Prize in 2002. How does this work, electrospray ionization? It's very different from MALDI in that it starts with a spray. And obviously a spray reminds you of a liquid. So we're not looking at a solid state here, we're looking at a liquid state. For that, we have a needle, and this needle is going to have a voltage applied to it. This voltage can be about 3,000 to 5,000 volts, so don't touch the needle, it can give you quite a sting. And that voltage is applied between the needle and the inlet of the mass spectrometer. Mind you, in my graph here, I put a right angle between the inlet of the mass spec and the needle. This is not necessarily true. You could also have the mass inlet here, but it actually serves the purpose of explaining it slightly better if we do it like this, and a lot of mass specs now have this orthogonal positioning. There is a barrier here which serves very little purpose. We'll see later on what it does. So what's going to happen now is that we're going to push our sample through, which is in the liquid state, through this needle. Now, if you have a very advanced setup, this might contain a buffering flow of nitrogen to make sure there is no turbulence inside this needle and that everything maintains a homogeneous flow. That's pretty sophisticated and it's a detail. The bottom line of what happens is the same thing that happens when you squeeze a garden hose when water is coming through it. Instead of a pure flow of water, the water flow now has to speed up to keep the same flux. This increased kinetic energy will translate into the ability to overcome surface tension, and instead of a stream of water, you're now going to have a spray of water. It's a very common thing, and again, when you've pressed the garden hose, you know how this works. Here's a nice picture of this in a mass spectrometer. You see the needle. There is here the tip of the needle, a jet with a plume of droplets results. And that's what I've rendered here for you. I've shown you here all these little droplets. Now, what is different with MALDI is that here we actually try to have the analyte molecules charged already inside the liquid. We do that by adding a little bit of acid to the liquid so that it actually has a pH of about 2. And that means that most of the sites will be protonated. Remember that very few things had a pKa below 2, so everything tends to be protonated, even the acids. And so the whole concept is that most of the analytes are already positively charged. We have droplets that contain peptides that for whatever reason we could not charge, or that contain no peptide at all, and they tend to be zero charge or neutrally charged. Now, here's where our electrical field comes into play. Because we have an electrical field, some of the droplets will feel the electrical field and respond to it. Other droplets will not. And of course, this has to do with the charge state. If you are charged, you move in the direction of the field. If you are not charged, you will not move away from your straight line. And here's what happens to the droplets that are non-charged. They will fly straight ahead because they are unaware of the electrical field, and they will slowly evaporate and ultimately end up against the barrier. That's what the barrier is there for, to make sure that this doesn't spray everywhere. It's a very small spray, but still. Now, where does the evaporation come from? Well, first and foremost, this is dissolved in water plus a small amount of acetonitrile to make it more hydrophobic. So that's easily evaporated, but we also heat the needle up. So it can be heated up to 60 degrees or so to make sure that the evaporation is more efficient and the droplets become ever smaller. And that's what you see here. The droplets become smaller, but then ultimately they do nothing. They just hit the barrier, and that's the end of their journey. Much more interesting is it to look at the positively charged droplets because they contain sample analytes. And let's see what happens to those. They feel this electrical field we've applied, and so they will start to move in the direction of the electrical field. So we get a beautiful separation between the droplets we don't want and the ones that we want when we have this orthogonal setup. You would not have this if you have the inlet straight ahead, and so you get a bit of contamination, if you like, from these droplets coming in. Now let's look in detail what happens. Evaporation applies to these droplets too, but something funny happens. So when you have a droplet and you're evaporating the solvent, so the water and the acetonitrile, the peptides stay behind. They don't evaporate. So in fact, if you have 2 or 3 positively charged peptides in this droplet and this droplet keeps shrinking, you're going to start to push like charges together. And what happens when you push like charges together? They start to repel each other, because you cannot push a plus charge onto a plus charge easily, just like you cannot push 2 magnets together very easily. And this repulsive force between like charges is ultimately going to lead to an overcoming of the surface tension, and is going to literally split the droplet apart. So in terms of surface tension, it's more exposed surface for the liquid, and it's biased against. But then because of the gains in free energy, because the charges are now completely separate, this can actually overcome. So what we get here is these droplets become smaller much more rapidly than these droplets, because there is an internal force, this charge repulsion, that makes the droplets fly apart. So we call that charge-driven fission of the droplets. They split into smaller droplets. Now this cannot continue forever. At some point, the droplet becomes so small that making 2 separate droplets is simply not an option anymore. What happens then is what is known as ion expulsion. A single ion, a peptide ion, just gets thrown out of the droplet and becomes an ion in the vacuum in the gas phase. And this is exactly what we want. So here, the trick is we have charged molecules in our solution. We spray it so that we can get a set of droplets. These droplets we try to separate in the ones that we don't want, uncharged ones, and the ones we're interested in that are charged. And then we allow the charge as quickly as possible to split into as small a set of droplets as possible, and then from these droplets to eject single charged ions in the gas phase. And ultimately, that's what we hope makes it into the inlet of the mass spectrometer. And of course, the size of the needle has something to say with that, the height of the temperature, and to some extent also the voltage, because it determines the traveling time. So these kind of things are important in electrospray. Another interesting thing that will come back, and it will become a bit of a nuisance for us, is that peptide analytes here tend to have more than one charge. They typically have 2, 3, 4, 5, 6, 7, or maybe even more charges. And the general rule is the bigger the peptide, the higher the charge will be. And so this is something that we will come back to. MALDI had a single charge. AZ has 2, 3, 4 plus charges. It has many charges on the peptides. This method, as you can see, is a liquid-driven method, so it's very easy to automate. If you have an autosampler that just can stick a needle into a vial and start injecting it into the system, after the vial is depleted, it can move on to the next one and the next one and the next one. So it's very easy to automate this and run it 24/7. It's one of the main reasons why this is super popular, and most people use this kind of method. It really allows you to run a mass spectrometer even when you're not around, 24/7, with a simple enough set of robotics that every lab can afford and has. So this Electrospray is now much more common than MALDI, primarily because of its ease of use and the ease of automation. Let's have a closer look at how Electrospray actually looks at peptides. Because if we were to inject all the peptides in a sample in one go, the mass spectrometer would be overwhelmed. Just as a back of the envelope calculation, the human genome contains 20,000 genes. Suppose we have a reasonably simple tissue that doesn't express more than 5,000 of these genes, which is, only a quarter of what the genome is capable of. These 5,000 proteins, if we cut them into smaller peptides, which we usually do with trypsin, that cleaves after lysine or arginine, which occur roughly 1 in every 20 amino acids each. So that's the combination is every 2 out of 20, so every 1 out of 10. That is how we come to this average length of 10 for a peptide. If we have these particular peptides cleaved from a protein, and we have 5,000 proteins, and I can give you the number for human genes is roughly 30 peptides per protein, that gives us 5,000 times 30, gives us 150,000 different peptides. That's not counting any modifications that might occur on the peptides, such as shortening them or adding chemical groups to them like phosphate or whatever. Now, this is an enormous amount of peptides, and if you throw this at once at the mass spectrometer, it's simply going to be overwhelmed. So we try to separate them out in time. And for that, we use a clever trick depending on the hydrophobicity of the peptides. We have two solvents, A and B. Let's have a look what's in there. So A is primarily water with a little bit of formic acid and some acetonitrile. Do you remember why we have these things? We need acetonitrile because peptides don't like pure water. They're a little bit hydrophobic, so we always need a little bit of hydrophobicity there to keep them happy, and that's where acetonitrile comes in. And acetonitrile obviously dissolves quite well in water because it's a little bit polar. Formic acid is because we want to make sure that all our peptides are positively charged. So this formic acid serves to reduce the pH and that we have well positively charged analyte molecules in our mixture. We start with that and with no B at all. And then over time we're going to mix in more and more B. What is B? It's essentially acetonitrile plus formic acid. The formic acid, of course, is there to keep the peptides positively charged, and the acetonitrile is there because it's super hydrophobic. And as we mix more B into this, so we kind of change the faucet from cold to warm, the water will become more hydrophobic. In fact, not the water, the solvent, because it will be less and less water all the time. It's very similar and very analogous to hot and warm water and a tap that allows you to mix the two. So let's keep on using this analogy. Let's call this cold water and this hot water. It's easier to understand. It's exactly the same principle in many ways. We have a solvent mixer that takes care of taking a certain amount of these and then mixing it together and pumping it on. And as we said, it will change over time. It will become more and more B, more and more hydrophobic, more and more warm in our analogy. This is then being pushed over a column, and this column is called a reverse phase column. The column is in fact very hydrophobic. So what's going to happen is before we use this, we're going to push the peptide mixture onto this column. And all the peptides are a little bit hydrophobic, so they see this hydrophobic column and they cling to it. They're going to hold on to that column. So then what we do is we connect the solvent mixer and we're going to start with nearly pure water, which is very cold, remember? So some of these peptides that are on the column will now say, I kind of like it here. I like this kind of temperature. I like this kind of hydrophobicity. It's very watery, and I happen to like watery. And they're going to let go, and they're going to flow with the solvent through the column and spray into our mass spectrometer. Whereas all the other peptides that don't like this particular temperature of water or don't like this particular hydrophobicity, they're going to stick onto the column. But then over time, we're going to have more and more of this hydrophobic mixture, solvent coming through the column. And then another set of peptides might say, this is more to my liking. They will let go. And so you see we get a staged release of the column depending on the amount of oiliness on the hydrophobicity of the solvent that we wash over the column. And this will change over time, and it will allow us to separate all the peptides in our sample over time depending on their hydrophobicity, with the most hydrophobic coming last and the least hydrophobic coming first out of the spray nozzle. So it allows us to do two things. We can automate it, we can run it 24/7 as a result, and we can couple it to a separation system online that allows us to separate the peptides into individual groups of peptides that are much more amenable to analysis because there's less that is clogging the mass spectrometer at the same time. The final thing I have to say about this is that there's different kinds of needles and sprays and columns. You have micro columns and nano columns. Now, what is the difference? If you take a needle diameter and then, of course, adapt the whole system prior to that as well, that is very, very small, you're going to optimize what is known as the surface to volume ratio. This is very important. A surface to volume ratio can be calculated conceptually. If you think of a droplet as a sphere, the area of a sphere, which is the outside of the sphere, right, the exposed surface, is 4 pi r squared. Okay, look it up in your mathematics textbooks. The volume is 4 pi r to the third divided by 3. So we have a cube relationship, and we have we have a square relationship and a cube relationship here. This is logical because the area compared to the volume, okay? Now, the time it takes to evaporate a droplet is related to the volume, because that's the total amount that needs to be evaporated, and the area. The smaller the area, the harder it is to evaporate something, especially for a large volume. Now, in a sphere, the two are directly related, and in fact, the relationship between them is 3 divided by r. It's a very simple mathematics. If you do a divided by v, you fill in the numbers, you will find out that it's 3 divided by r. As the droplet shrinks, there will be more surface compared to volume in this ever-shrinking droplet. So a small droplet evaporates faster than a big one. You know this from experience. If you have a pot full of coffee, it will take a long time before the coffee is cold. But if you were to pour the coffee out on the tabletop in a very thin layer that has a huge surface area, it will cool down very, very quickly. This is why if you want to cool your coffee down, it's better to pour it into cups already. The cups will cool down much faster than the big chunk because the volume to surface ratio is different depending on the size of the container. This is exactly the same. Bottom line is, smaller droplet will evaporate faster because the surface to volume ratio that is inversely proportional to the size of the droplet is more beneficial. It's bigger area to volume. Which means that if we have a nano spray, you get really small droplets that evaporate very quickly. And if they evaporate quickly, you very quickly get charge-driven fission and charge-driven ion expulsion. And ion expulsion is what we want. So you gain sensitivity. A smaller amount of analyte will yield detectable ions in the mass spectrometer. With a micro column, the droplets will be much bigger and the sensitivity will be less. Because remember, any ion that does not get exposed does not make it into the machine and does not end up analyzed. The downside, so why doesn't everybody use a nano spray? Well, the downside of the nano spray is that it creates a lot of technical issues. Nano sprays are really, really small needles, which means a lot of back pressure, a lot of heat generation, and a lot of probability of getting clogged. So nowadays, people who want to be very sensitive tend to use nano equipment, and a lot of researchers do. But when you do routine analyses that you have to run 24/7 and where the sensitivity might not be the most important thing, the microsystems are much more reliable. So it's a trade-off between sensitivity with very small droplets that allow you to see the small amounts of analyte because they end up in small droplets and get expelled, or you want to have more reliability with a microcolumn. It depends a little bit about what you want to do. Both systems are good and both systems have their benefits. Now, I just have to finish off with one last thing. You may know this particular fellow is the Cookie Monster. And you know what the Cookie Monster likes? The Cookie Monster likes cookies. Now, I don't know if you've ever been to a scientific conference, but I've been to quite a few. And there is this very strange ritual that takes place between lectures. It's known as the coffee break. Now, in a coffee break, everybody races to get to this coffee break. Not because of the coffee, although that's really nice, but because of these cookies. Everybody wants these cookies. Now, imagine this. We're all sitting in a lecture theater, and suddenly there's a coffee break. There's 20 of us, but there's only 5 cookies. Who gets these 5 cookies? If you think about it, it can either be the fastest people, because they run to the cookies first, or it might be the strongest people, because they can elbow everybody else out of the way on the way to the cookies. The bottom line is, not everybody ends up with a cookie, and it depends on the properties of the individuals who ends up with a cookie. The same thing happens for our poor ions when they get ionized in MALDI or EASY, because what is going on there is a very similar process. There simply isn't enough charge to go around for everyone. And these ions, these sample molecules, they're not ions yet, these sample molecules are going to have to compete with each other for whom gets to have the charge. And there too, there are certain properties that make it easier for some of them to get to these charges than for others to get to the charges. You may remember that I told you when we were mentioning MALDI that there are some peptides, those that contain aromatic residues because they fit in with the layer cake better, they ionize better. These guys in MALDI have a distinctive advantage to become ionized. And so there we see that this problem of not enough cookies or not enough charges leads to competition between ions, and some will have a benefit a priori compared to others. We call this competitive ionization. It happens, of course, in EASY as well, but the problem with EASY is that it's very difficult to predict which ions will behave better than others. What makes it even worse is the following. Suppose we're in this room, this lecture theater, and a coffee break starts and there are only 5 cookies, and we see that the fastest people in the room get all the cookies. Now, can you imagine what will happen in the second coffee break? We will have exactly the same situation. So the same fast people will end up with the cookies. It's predictable. But what if we swap out everybody else in this lecture room and replace them with the Olympic finalists of the 100-meter sprint? Do you think that the people who had the cookies first will still get them when they're faced with such stiff competition? I actually think the Olympians will win out, supposing they're interested in the cookies in the first place. But what this teaches you is that it's not just how fast you are. What matters is how fast are you compared to your current surroundings. I can put you in a situation where you will for sure get all the cookies. I can also put you in a situation where you will get none of the cookies. So what matters is the situation you are in, the company you keep at the time of ionization. The same for the peptides. We can have a peptide ionize extremely well when it's by itself, put a few other peptides in there, and the ionization will go completely crazy. So it's very, very difficult to predict a priori which peptides will steal the charges. But it's quite important because, as we said before, if you don't get a charge as an analyte, the mass spectrometer will never even see you and you won't stand a chance to be detected. So ionization is crucially important, and competitive ionization is a really big problem when you try to get as sensitive as possible, as deep as possible. One of the solutions we talked about was nano-electrospray, if you will remember, that make these smaller droplets, which essentially translates into more cookies to go around for everyone. But still, it's not a panacea. So always keep in mind there are limitations. Whatever does not ionize does not make it into the instrument. And there definitely is something called competitive ionization. You don't want to be in the coffee break with this guy. So thank you very much for watching this particular lecture. Next lecture we'll talk about analyzers. Now that we have the ions in the gas phase, how do we analyze them? Thank you very much and see you next time.